Right, welcome. So you're back for more, eh? What are you getting the itch? In this video, we're going to be taking a look at some of the ways that malware tries to hide itself, or make it harder for you, a pesky analyst, to examine and dissect it. We'll be taking a look at how malware can implement anti-debugging or anti-analysis features, or even obliterate itself if it detects that you're looking somewhere where it thinks that you shouldn't be. It's very cool stuff, and you know what? This video itself might accidentally follow suit and do a self-deletion cosplay because of the subject matter, and how much YouTube despises slippery slope videos like this, which is why, mandatory disclaimer alert. This video is solely meant for educational purposes. Through covering these techniques, we'll uncover how certain malware tricks or bypasses antivirus or analysts, more so the analysts. We will talk about antivirus and EDRs, but we're not going to cover how to bypass them in this video. Shut up! Just so that you're aware of these inner workings and you can look out for it. Never use these techniques or anything that you might find on my channel, blog posts on the internet, or whatever it is, for malicious purposes, and only test against things that you have explicit written permission for. We won't focus too much on bypassing antivirus, but we'll definitely talk about it briefly since we're already on the topic of defensive measures. You know, it's actually a quite common question, but I hear this a lot. Why would you want to start learning malware development? Isn't that just solely for the criminals? I mean, what good is malware? Well, as the great philosopher Diogenes once said, how in the fuck else are you supposed to defend against something if you don't, one, know what the aforementioned thing is capable of, as well as its limitations therein, and most importantly, two, how it works. We learn this stuff not to wreak havoc, pun intended, not to wreak havoc on the innocent, rather to understand what the bad guys are doing so we can make our defensive solutions that much better. That's why you'll even see some of these techniques being talked about in depth from actual defensive solutions like Sentinel-1, for example. Not because they're trying to shoot themselves in the foot, but because, again, it's important for you to understand something almost at an intimate level in order to destroy it. Otherwise, how can you possibly defend yourself from it? That's not all. In terms of audits and engagements of someone's security posture, we also develop our own malware to give our clients the best chance of a proper test. If you try to load Mimikatz, Rubius, MSF Venom payloads, or anything that's heavily signatured like that, then yeah, most likely your clients would detect that. But what about something that hasn't been signatured yet? What about something custom and unknown? That's a huge fucking thing to just leave out of your testing, don't you think? That's where malware development is really big, or most would even say required in red teaming. A ton of our offensive tools are heavily cataloged and detected right out of the box, which is where the malware development skill set comes into play. But I digress. Just know that we're only learning this as ethical hackers, and using this maliciously is not allowed, and I do not, nor would I ever condone such a boneheaded move. I mean it. Use your powers for good, guys. Anyway, shh. Do you hear that? Mr. Rat?
I'm sad, yo.
What's wrong?
I'm in mental anguish, yo.
Why, buddy? What's going on?
Everyone seems to be so good and so far ahead of the curve. Meanwhile, I'm over here trying to figure out what caused Microsoft to do this.
Wait, okay, so you're telling me you're completely lost, you don't know where to even begin with malware development, and most importantly, you're a complete beginner? But why didn't you just say so, Rat? Introducing Maldev Academy. Gone, Mr. Rat, are the days where you're left behind, because Maldev Academy is a brand spanking new module-based learning platform founded by two legends in the field, Mr. Docs and Null. You will be brought up from your current predicament to a god, a rat amongst men. The learning modules are organized in a linear fashion. You'll start off learning the extreme basics like the basics of C and the Windows API, to API hooking, syscalls, anti-detection, all the way up to some crazy stuff like hardware breakpoints, anti-DLL unhooking, custom protocol handlers, and even more planned for the future. You will get access to a virtual machine with all the necessary tools already set up, as well as the source code for the modules on there. There are constant updates with so much planned for the future, a thriving Discord community filled to the brim with awesome people constantly learning and sharing, not to mention all the stuff we get from the co-founders themselves, just casually dropping in tidbits there and there. And even this dork is here, providing challenges to help you build and implement what you've learned. Please, Spider, give me back my car keys, please, I have to pick up my son. There's a plan for everyone, and just for you wonderful bastards, we've gone ahead and given you 10% off if you use code CROW10 for a limited time. As you can see, whether you're a complete beginner or a paprika seasoned veteran, everyone can gain something from the Academy. Thank you so much to Maldev Academy for graciously sponsoring this video. As someone currently going through the modules, I wholeheartedly recommend it. Again, make sure to check out the pinned comment below or the first link in the description to get 10% off your order using code CROW10. Now, Mr. Rat, how's about we get back to the video? Rat?
Not now, bitch. I'm making my own seat too.
Perfect. First things first, we need to talk about what AVs even are and how they work. After that, we'll take a quick look at the differences between a typical antivirus solution and an EDR. Presumably, you already know what an antivirus is due to how prevalent they are in pop culture, or even better, maybe you can even name a couple, like this like this wonderful, amazing bitch. An antivirus is a defensive solution that is specifically designed to detect and remove malicious software from your device. Windows Defender is an example of an antivirus, perhaps one of the most famous examples aside from like Norton or some shit. It does a bunch of hashtag quirky little things in an attempt to hashtag protect your ass from perilous heathens. We'll cover some of the common ways that it protects you, but generally speaking, an antivirus uses the following for defensive measures. An antivirus will read or scan your file and compare it to a database of known signatures to see if what you have there is malicious or not. These signatures could be known hashes of some malicious programs that your file gets compared to see if there's a match, which would let the AV know like, oh hey, this file is malicious. Wait a minute. This file is malicious. Or it could even be checked against predetermined characteristics or attributes of known malware or rules that your file matches with. It could get flagged like that too. These characteristics and rules could be something like human readable string, some sequence of bytes, the file type itself, the size of the file, a ton of other metadata, and etc, etc. A couple of you nerds might be thinking, well, why don't we just use the file hashes themselves to check for malware all the time? And I really like the way that this blog post from Sentinel-1 says it best. Signature-based detection offers a number of advantages over simple file hash matching. First, by means of a signature that matches commonalities among samples, malware analysts can target whole families of malware rather than just a single sample. Well, signature-based detection, as prevalent as it is not without its cons. So let's be bullies and point out its insecurities. Number one, signature-based detection primarily only works well if you have a signature to compare your bastard file with. Secondly, although it's miles better than just hash comparing, it's still pretty easy to evade signature-based detection by simply just tweaking your malware a bit. Yeah, back in the day, malware was coming out slower than my videos, so keeping a database of signatures which contains hashes and rules for these malicious programs was pretty effective for a while. However, at the rate at which malware comes out nowadays, it's simply just not efficient or possible to write effective signatures for all these unique malware samples that come out. Polymorphic malware really shines here, since the whole premise of polymorphic malware is to create malware that's constantly changing its identifiable features in order to evade detection. Today, right now, live, you could shoot your computer with a Desert Eagle hundreds of meters away, yet some new unique malware that no one has ever even heard of will probably end up reaching it first anyways. That's how common it is now. Not to mention that if a signature rule set is public, it's just a matter of time before malware developers dance around it or adapt to it. Oh, and last but not least, the fact that most attacks nowadays are fileless anyways, meaning that instead of dropping your payload onto disk, which can very easily be detected, you're most likely going to be executing your payload in memory, never having it touch disk. This cripples signature-based detection that relies on file stuff. So as you can see with all of these points and more that I haven't even covered, signature-based detection isn't so based after all. It's definitely better than using nothing, and AV providers will use them. But long gone are the days where you could just get by somewhat by just relying on this. So this brings us to heuristic detection. With signature-based detection covered, now we can move on to the meat and xylophones of these detection mechanisms to combat the sour taste that signature-based detection left in the sarlacc pit that is your mouth. A heuristic model is adopted. And according to Kaspersky, according to this is specifically designed to spot suspicious attributes or characteristics that can be found in unknown new viruses and modified versions of existing threads, as well as known malware samples, which is exactly what the static signature-based detection was lacking. So that's cool and all, but how does this work? Well, there's two ways underneath the blanket term of heuristic detection. There's static heuristic detection and dynamic heuristic detection. Static heuristics, this is a method all about file analysis. The file in question is decompiled so that the source code of it can be tested against known viruses in the heuristic database. If a portion of this examined code matches the database, then it's flagged. Dynamic heuristics, in this method, your file is sandboxed and isolated to see what it does and how it executes without putting the rest of your system, devices, or networks at risk. With this section, we're not looking for the file itself explicitly, more so what the file does or it doesn't do, etc. when it runs. The main focus here is behavior. When you start out in your ethical hacking journey, you'll no doubt be faced in situations where you either have to simply encode your payload or something to get your malware onto the target. And while it's great for getting past those pesky static detections, what a lot of people forget is that there's this whole other manner of heuristics that deals with behavior. It won't mean a lot for you as a hacker if you can bypass the static detection, only for you to end up with some signature and staged payload like a reverse shell from MSF Venom or something. And not to mention, your target connecting back to you at some arbitrary port through TCP all willy-nilly. I think you get where I'm getting at. Again, this is very high level, but it's necessary for us to cover AVs and their quirks a bit. You're urged to do some research as well. There's a lot of resources on antiviruses and their mannerisms and their quirks and their toxic traits and all that stuff. So let's be really clear here. I'm not advocating that all of you uninstall your antiviruses in gamer rebellion because you think I'm denouncing all AVs. Sure, some AVs are better than others, but that's not my point. No, not at all. We're allowed to be critical and point out the flaws of the things that are supposed to protect us if it means that we can work towards making it better. And certain AVs are pretty decent at protecting most people. If said, most people already are pretty cyber hygienic to begin with. So sure, it's pretty easy to bypass Defender as it stands, but I'd much rather have something than be bare and naked on the disgusting moldy sewage warfront that is the publicly facing internet. With that being said, it's important to note that antivirus isn't without its fault. Obviously, right? Aside from the heuristics based evasions, both static and dynamic, it seems like in the modern day with modern threats, AV just might not be enough, or is just a generator of false positives. For example, one of my bestest friends ever, Zor, who you should go subscribe to right now, once showed this simple program that just prints iterations that got flagged by Avast, but a fucking injector was fine. Again, it's nothing perfect, but you can see how AV sometimes just melts when it comes to unknown threats out there. And that sucks because unknown threats are primarily the biggest concern for most employees or employers, especially when it comes to the big companies, and because of that, AV can seem rather lackluster. One, because of all the points that we've mentioned thus far, and another because AVs are really meant for a per device model, which isn't of much help to organizations with infrastructures comprised of hundreds if not thousands of devices or endpoints. And this brings us to EDRs. Well, what's an endpoint to begin with anyways? Well, you could say that anything connected to the network is an endpoint. If you're a company with a lot of laptops, smartphones, servers, remote controlled pip vipers or some shit, those are all endpoints. And TLDR and EDR is this guy on turbo roids, rage symptoms and all. And EDR typically does everything an AV already does, except with way more ferocity and way more efficiency. Whereas antivirus deals with known threats primarily, which again can just be bypassed using polymorphic techniques. EDRs are more focused on detecting unknown suspicious threats as well as known threats. They're part of the real-time detection cult, and they have a much wider protection surface since the whole point is to provide security teams a centralized area from which they can monitor an attacker's move as if they were shoulder surfing them. And most importantly, they try to protect a ton of devices. Some EDRs even use AI or machine learning algorithms, that's like that nerdiest programmer shit I've ever said, to learn from their efforts in order to improve an EDR's accuracy, to limit the number of false positives. That's not to say that you won't get false positives, of course you will. And some EDR solutions like Sentinel-1 even claim that AI and machine learning effectively identifies 0 days, and so much more. And this video isn't intended to be a pseudo defensive solutions tier list video, so you're urged to go out and read more about this on your own. But some of the ways that these defensive measures perform their defensive tasks is really interesting. Antivirus is something that really complements an EDR as well, which is why you might see AVs and EDRs used in conjunction for protection. With that being said, enough theory. This video is already long as it is, and we haven't even programmed a single line of code, so let's take a look at some of the techniques that we can employ. Remember, security isn't something that can just be outright bought. There are products, yes. However, security itself is a mindset, so with that roughly covered, let's figure out how we can mess with some analysts. We want to make the lives of analysts as difficult as possible when we make our malware. This brings us to our first anti-analysis technique. Surely, the majority of you already know what a debugger is, right? They're just things that let you examine what's going on inside of an application. Well, as an analyst, you want to be able to examine malicious software, and you're typically going to be doing that through a debugger. The problem with that is semi-capable malware will often do its best to make your life as an analyst absolute hell. Malware typically wants to do its best to 1, hide from you, and 2, if found, make examining it as hard as possible for you. The worst part is that the most basic implementations of this anti-debugging behavior that malware uses can be done with just a single function. However, there are more ways to do this, definitely. Speaking of which, let's look at this extremely easy implementation. A super simple check that we can do to see if we're being debugged is by using the aptly named IsDebuggerPresent function. Here's what this might look like. Because we know that this function will return true if it's being debugged or false if it's not, we can set up a check like this, and we can see that if the debugger is not present, we can run our super dangerous malware, right?
What the fuck? Are you trying to kickstart the apocalypse? I get we're making malware and shit, but message box W as your payload? Isn't that a bit extreme? You belligerent miss-
Oh shit. Yeah, sorry, I'm getting ahead of myself. Okay, nice. So we can see that if we just run this program after compiling it, normally the hyper malicious code will get executed. However, if we start this by debugging it, and remember you can do this with any debugger, you don't have to just use Visual Studio, we can see that our malware shits itself and it won't run. So you can see this is very easy and it's just one function. And this is cool and all, but you should also put yourself in the shoes of the defense. Think about what an analyst might think if they try to debug your program and see this. So another less suspicious thing that you might do is if a debugger is present, have the program run something completely harmless, like forcing the capacitors of your target's motherboard to explode. I'm kidding. Alright, let's continue. Now this seems very easy and super straightforward, and it's because it is. However, as you might have guessed by now, having your malware call a function like IsDebuggerPresent inside of it is so fucking suspicious and not even humorous, okay? This is like a bank robber trying to figure out how many cameras there are in a bank by asking the fucking security guards. So how about a more inconspicuous approach? We will effectively be doing the same thing, except at a lower level, such as to not bring a giant gamer room LED spotlight on us. Another little alternative for the IsDebugger function, say you wanted to check if a different function, a remote one, something that you didn't start, you can call the check remote debugger present function, which does the same exact thing, and this is how it might look like. And another thing that you could even do is call a lower level NT-API function called anti-query information process to get some information about our process, including a pointer to our target's process PEB structure, but we'll cover the PEB very shortly. Don't worry if this is confusing right now because we're gonna go into depth very shortly here. This function and the other functions by extension will make much more sense once we've covered two vital structures related to processes and threads. Knowing these structures will let us understand how these debug checking functions even work to begin with. And you better be excited right now because we are about to start reverse engineering. At this point, you should be very familiar with what a process and a thread is. If not, go watch the first video in our series for malware development. We need to talk about what the PEB and the TEB are and how some functions like IsDebuggerPresent or GetLastError just boil down to reading values from these structures. When a process gets created and the main thread runs and executes and all that jazz, there's this very important structure that houses some information about that thread, and this structure is called the thread environment block. From this structure, we can see some of the members in it. You can see a lot of this juicy information. You remember how in the last video we used the GetLastError API to tell us the error code so that we can look it up in documentation? Well, that GetLastError function, all it does is read the value from the tab at the last error value member. That's all it's doing. You can see it right here. You can see how some of these Windows API functions just end up reading from these very primitive structures, and not primitive in the sense of complexity or the lack thereof. Trust me, these structures can get very, very complex, but in terms of how early on they're present, maybe primal was a better word. Well, this is great, but let's dive deeper. Where exactly is this structure to begin with in memory? In Windows, there are certain registers that will always hold a reference to the TEB, and by extension the PEB structure, which we're going to talk about soon. These structures are stored in the FS and GS segment registers. The register that's used is dictated by the architecture you're on. On 32-bit, the TEB structure is going to be located in the FS segment register at an offset of 18. On 64-bit, it's located in the GS segment register at an offset of 30. Also, note that on the 32-bit scenario, you might hear of TIB in the thread information block, and the TIB is also known as the TEB. These terms are interchangeable, they're the same thing. If we revisit that GetLastError function boiled down to see how it's reading from the TEB, if we look at the NT-current TEB function itself, we can go one step lower and see what this function is doing. As you might expect, yes, it's literally just a pointer from the FS register at the 18 offset, which we know is where the TEB is. If this was on 64-bit, that would be a read GS keyword at offset 30. Because this is being referenced by the FS register, we know that this is for 32-bit. Another thing you might notice is how barren the TEB structure looks like when you consult the MSDN versus when you manually dump it from something like WinDebugger. You get it from a site like Virgilius. And the first thing we notice is how itsy bitsy this one is here. And after noticing that, we can see how a lot of these fields are just set to reserved, and Microsoft, I found, does this for a lot of the undocumented stuff. See, Microsoft doesn't particularly like us doing this stuff and getting our hands dirty with the lower level stuff. It doesn't like us poking around. When we eventually replace the IsBeingDebugged BeingDebugged function with our own alternative, we'll see that Microsoft doesn't recommend this, and they'll tell you not to use it like this. Well, from their side, it's pretty easy to see why they do this. Firstly, the unspoken rule of undocumented internals is that they can and eventually most likely will change without prior warning. And some structures gain new fields with newer versions of Windows, and a lot of syscall numbers change with versions. And we'll do a little spoiler alert and look at the PEB structure from the MSDN to see what the reserved word actually means. And it's just, firstly, they give this warning. The structure might be altered in future versions of the Windows. And then for all the reserved members, they just say it's reserved for internal use by the operating system. This is basically Microsoft saying, and I'm just paraphrasing here, hey dumbass, we don't want you messing around with this stuff. Leave it for the goddamn computer to handle. This stuff is prone to change without warning, as is the case with most of the low-level undocumented stuff out there. Does this stop us? Nay, not at all. In an attempt to consolidate our learning, what we're going to do is create a new project in which we create our own rendition of the GetLastError function that we were using in the previous video when we were making our injector. And we're going to do this to understand exactly how that function works and how the TEB is tied in with all of this, or at the base of all of this. So we can just start off by making a new project. Because we're going to be using assembly in this project, there's going to be a little bit of setup that we have to do in order to get our project, capable of using assembly. So what we have to do first and foremost is go right click on our project, go to build dependencies and build customizations. In this menu, in this box, what we're going to do is enable the MASM. This will let us use assembly in our program. And now we're going to have the option to select the Microsoft Macro Assembler option for any assembly files that we choose to add into our project. Speaking of which, what we're going to do is make an assembly file that's going to get the TEB for us and then read in that last error value should a function fail, which we're going to purposely make fail just to prove our point. Call this LastError.asm. And before we can actually start incorporating this, we have to make sure that it's set properly. So right click on this, go to properties, and if this item type isn't already selected as Microsoft Macro Assembler, sometimes it might be, for me in this case it was already, all you'd have to do is go to the drop down menu and find it. If you didn't enable the MASM selection in the project build dependencies, this option will not show up. So make sure that's enabled first before trying this, and then select it. Once that's done, you should be able to start. Now unfortunately, this is not going to be an assembly 101 or an introduction to assembly programming. With that being said, I will try my best to explain what's going on while still, making everything compact. So what we're going to do first is create a code section for our assembly program. And then in this code section, we're going to start making a procedure, which you can just think of as like a little function. We're going to start off by creating a procedure that gets the TEB and puts it into a register. And then after we get that procedure done and made, we'll make a new procedure in which we retrieve that last error value member or field from the TEB. So what we've done here is move the address of the TEB, which is located in the GS register at the offset of 30, into RAX. So we've effectively just retrieved the TEB. And somewhere down the line, you might see that people don't use any offset when they get the TEB, and that's perfectly fine too. You could do it like that. As this article says, it's not common to do it, but you can do it. And for all intents and purposes, it should work fine. It's just that if you self-reference it or get the actual member of the TEB itself, then it allows for other things like pointer arithmetic and stuff like that. But I just like doing it this way, so that's what we're going to do. So with this procedure defined, now we can start making another procedure that will get that last error value from the TEB. With this done, we can use the end keyword to let it know that we're done with this, and let's talk about this procedure. So in custom error, what we're doing is defining a procedure in which we first XOR out or just create a blank slate for this register, because this is going to be XORed by itself. It's going to zero it out, and then we call this procedure. So remember, all we're doing here is getting the TEB. After we get the TEB, what we're going to do is move. The TEB is located at REX. The reason we chose 68 to move into the EAX register was because 68 is at the offset at which this last error value member lives, and that's what error code that we retrieve. And we can see that it's of the type ulong. So we're going to do a dword pointer. Oh, so yeah, that should be end procedure. Well, now what we can do is make a C file in which we will actually utilize these two procedures. And this is straight from assembly. Isn't that cool? And also, don't worry too much. You can find all of this code that we talked about in this video in the description on my GitHub. I'll have it there, so don't worry too much. All right, now let's make our C file. Okay, and I don't like putting all my includes and everything in my C file, so what I'm going to do is also make a header file. You don't have to do this, you really don't, but I just like to do it like this. In here, I'll include all the libraries that we're going to need since we're doing a bunch of Windows shit. We're going to have to include the Windows header as well as another header that we'll talk about once I include it. So the reason that I've included WinInternal is because without WinInternal, what we'd have to do is supply our own structures for the TEB and the PEB, and those can get very, very tedious, but I do urge that you go do that just so you get a better appreciation of these structures and what those structures require. Next, I'm just gonna put out some of these macros that I've been using, lifesavers for debugging. Okay. Very nice. Now, in order to use the assembly procedures that we've defined in the assembly file, we're going to have to use the extern keyword to let this program know that it's supposed to get it from somewhere else, more specifically from here. So we want this function to return a pointer to the TEB, because that's what we're doing, we're getting the TEB. So I've just set that as its data type, and it doesn't take in an argument or anything, so we're just going to close that off by doing void inside of the parentheses. The next one is the custom error. So the reason it's a D word is because if we come back to this or any other thing that you dump the TEB from, it's going to show you this as the type you want, right? Or unsigned long. And we already know that the D word is just a fancy way of saying unsigned long. So instead of D word, what you could do is just put that there as well, but I mean, it's up to you. I'm gonna just do this. With that done, let's start off by printing the value of the TEB after we get it, just to make sure that we actually got the TEB. After that, we will purposely make a function fail, and the reason we're doing this is because we want to compare our custom error function with something that we will know that will work, like the GetLastError function. So let's do that. Okay. I know this formatting looks insane and crazy from this, but it's just the way I like to format my structures or functions, and whatever values get stored in them, like my handles to my processes and threads and handles to modules or addresses of functions. I like to do this, and this should not be that. This should be this. So we're going to be printing out the value of the TEB here. Let's actually just see if that works real quick. Okay, cool. Yeah, that's really cool. So we can see that it's working. This is the address of the TEB. At this point, we're no strangers to opening handles to processes, so that's what we're going to do, except in this one, we're going to make it purposely fail. So for the PID value, we're going to set it to something completely wrong. Right, so this is not going to be a legitimate process ID, and so it's going to fail. And we know what error value to expect already because we've talked about this before. Remember, if you don't have no idea what I'm talking about, go back to the other videos and watch them. We know from our previous time in which we got a bad parameter to this function, it's going to return the following error code. It's going to return the error invalid parameter error code, which is just 87 decimal or hex 57. And this is the value that we're going to be looking out for to see if our function returns the same thing, which is just this. Why did I have this returning exit failure from the get-go? What? And that should be it. So what we're doing is we're going to check to see if it's going to be null, which it's going to be. We know it's going to be, because if this function ever fails, what it's going to return is null. In the case that it inevitably fails, we're going to say, okay, it failed. This is a good thing, don't worry. And then we're going to print out the value of our custom error function and then the value from a GetLastError function. And if these two match up, we'll see that it's matched. Our function will be working properly. Otherwise, something went wrong, and just print out what the value is actually supposed to be so that we can troubleshoot. Let's run this and see what happens. Cool. Okay, so yeah, it works perfectly. We get a value of 57 and it prints out a value of 57. That's working fantastically. And this isn't just a fluke. Say we wanted to get access to a privileged process, something like the process of system, which is going to be referenced by the process ID of 4. What we're going to be expecting is an error code of 5 for access denied. So let's see if that works. It works incredibly. There we go. And yeah, just to prove it, 5 is access denied. So yeah, this is working properly. Amazing stuff. Another important member that we can see within the TEB structure is the PEB structure. And this is a very, very infamous and shiny structure for malware developers and analysts alike. You'll see this reference a lot as you progress on your journey. The process environment block is a structure very similar to the PEB. It gives you a user mode representation of the current process. It has a lot of members, and it can let you figure out a lot of cool things. We see that on 32-bit systems, the PEB can be found from the PEB at an offset of 30. In other words, we can find the PEB structure on 32-bit systems in the FS segment register at an offset of 30. What do you think it is for the 64-bit? Let's give you a second here. Let's just guess. That's right. On 64-bit, it will be located in the GS segment register at an offset of 60. Now, what makes this structure so special? Well, let's look at some case scenarios. You want to figure out what command line arguments the process was given? This member tells you that. You want to figure out what DLLs and modules have been loaded by your process? Well, look no further than this. And there's a lot more. One member in particular that's going to be at the vanguard of our purposes is the BeingDebugged member. This member is located in the PEB at the offset of 2. So, you know how I mentioned that the IsDebuggerPresent just reads a value from the PEB structure? Well, I wasn't lying. Take a look at this. We get the PEB structure, which is just going to be reading in a value from one of those segment registers depending on what architecture we're on, and then it checks that BeingDebugged member from that structure, and it's Boolean. It's being debugged or it's not, and we can see that all along. This function was just reading the value, and instead of calling IsDebuggerPresent, we can instead just program something very similar, so that way we're not calling the super suspicious API. And there are many other ways we can go about this. One common way is doing the following in a C or C++ file. Right? We just get the PEB here. We read the value from the GS register at the 60 offset, which by now we know is a PEB on 64-bit. We typecast this to a pointer to this PEB structure so that our PEB will now let us interact with the PEB and subsequently its members. So let's begin by checking the value of BeingDebugged member and see if we're being debugged or not. Remember, this is exactly what the WinAPI function was doing all along. And now, as expected, if we run it without debugging, it will report back to us as such. However, if we run the debugger option, it will tell us that we're being debugged, and all without calling that IsDebugger function. Now, another thing that we could do is just get the PEB directly using assembly in our program. Alright, here's where we get started with some direct PEB assembly bullshit. What we're gonna do is we're going to get the PEB straight up from assembly. Luckily, we've already covered how to get our project ready for assembly development, so I'm gonna skip over that. And this is pretty cookie cutter stuff from the PEB. Instead of getting the PEB, what we're gonna do is just get the PEB and then get the BeingDebugged member from that PEB. So let's do that. Okay, in our assembly file, start making out the code. Alright, that seems to be good. We know that this member is just a char size or byte size, so that's we're doing a byte pointer. We're getting the PEB, and then we're checking this member, and whatever member it is, we're gonna do something from here. So remember, because we're using ASM, we're gonna have to externally call it. Okay, you should understand why we're prefacing these two. Alright, let's set up the main function. And I'm sure this can be streamlined and stuff. I'm by no means an expert in assembly programming. And we'll also have a payload here. And that stupid rat is in here, so I can use message box W if I want to. Okay, with that we should be good to go. Let's start this regularly. Oh, damn. Okay, yeah. Cool. We can see that it's not being debugged, right? That it will execute our payload. However, if we start it with the debugger detected, and all without calling the IsDebuggerPresent, we just straight up emulated that function by using straight up assembly. That's cool, awesome. And this is where I'm a level with you, okay? It doesn't really matter if we get the PEB like this instead of using the bloated WinAPI function, because an analyst will see this line, and anything that's usually referencing the GS register at 60 offset or the FS at 30 offset, a decent analyst will know that the PEB is being referenced or being populated somewhere. So again, it's just one technique that you can use. And now the question arises, it's very easy for us since we're debugging our own program, but how in the hell can we check to see if the BeingDebugged member is enabled for another process that we don't own? Well, let me introduce you to the NT-query information function. I won't cover this function in depth, as this will be your homework from this video. Although note that you're going to have to touch up on your NT API, NT-DLL understanding. You can get information about the process, including the PEB of the target process. And once you have the PEB, you should just be able to check the BeingDebugged value to see if the remote process is being debugged or not. Again, that's left as an exercise for you to go and perform. Now, let's discuss how we as analysts, not developers, might be able to bypass this anti-analysis technique through a means of patching. What if we want to be anti-debuggers, hey? What if we want to put on our little blue teaming lantern rings and force some malware to run while it's being debugged, but it's being pesky and it keeps exiting before we can do anything? Well, fear not. As you know by now, most of these anti-debugging functions or whatever just boil down to the PEB at the offset of 2, i.e. the BeingDebugged member. So all these functions are just reading this value to see if it's being set to 1. So if our malware is doing the same thing, we can just patch that member to 0 and trick the malware into thinking that it's not being debugged when it actually is. I'll do this for a local process, but the logic is the same thing for a remote target process. But again, I'll leave that for you to go and tinker with. And we're going to be doing this in assembly. Now, the great thing about this assembly patching thing is that 95% of our groundwork is already done for us over here. We get the PEB. The only thing that we have to do in assembly now is check to see whether being debugged is 0 or not. And if it's not 0, we'll jump to a different section in this code, which we will program out. So firstly over here, we're going to test to see if EAX is 0 or not. And if it's not 0, we're going to do a jump not 0 to this patch section that we're going to program out. And there we go. What we would have done is gotten the PEB overriding what's on there on being debugged with a 0, effectively patching it. So if the malware was to detect if it was being debugged or not, if it's checking through being debugged, it's not going to show up as that, and we're going to bypass the check. So let's see how we can program that out here. Firstly, I think we should change the name of this because it's going to get kind of confusing if we're trying to do that. So I will just call it PEB Patcher or something. Now what we'll do is the classic little PEB member check instead of check debugger. Remember, it's pretty much doing the same exact thing, honestly. And because we want our malware to run even though we're patching it, if for some reason the PEB BeingDebugged isn't set to 0 after this patch, we'll return exit. At this point, yeah, we'll be able to check the before and after. So we'll see that if we start it with a debugger, it's going to detect that it's being debugged, obviously, right? But after that, it's going to go into our PEB patcher procedure, which is going to test it to see if it's going to be set to 0 or not. And if it's not set to 0, meaning that it is being debugged, it's going to jump to this patch area and patch it, after which it should print out that, should rename these. Now let's see. Okay, so amazingly, we started it with the debugger. We can see that the debugger is currently running. See that it's being debugged, and then it goes into the patch, and it patches it. At this point, the malware is none the wiser, and it runs, letting us analyze it. Now, I know with this being something that we program out ourselves, a lot of you might be wondering, Crow, why are you programming this out, and why are you telling us this useless information? I mean, you literally have the source code of the malware. You are in control if it runs or not. I get what you're saying. And the reason I'm teaching you this, as useless as it might seem, is because even if it's for a remote program, something that you do not start or you have no control over, the way you're going to be doing this is the exact same way. But we're done with this now, and we can see that we've just implemented a custom PEB patcher in assembly. That's really fun stuff. As background before delving into this arcane knowledge, let's see what happens if we attempt to delete a file while it's opened somewhere or currently in use. You've probably run into this before, where you're trying to delete something but it's being used somewhere. Where the fuck is this file being used? You think to yourself, while cursing out computers in the same breath. Well, yeah, you're not able to delete a file if it's open somewhere or in use. We can show it off this way, or we can even do it with the Windows API itself and see what error code we get. So what, are we doomed? If our malware detects that it's being debugged, are we condemned? Are we destined to leave it in the hands of the, sorry, I almost barfed. Leave it to the hands of the analysts? Those heathens? Well, of course not. Otherwise the video would end here. We'll look at a really cool technique of anti-analysis, self-deletion. And in order to do this, we must really quickly talk about NTFS. I know this seems like it's coming totally out of left field, but it'll make sense, don't worry. NTFS, or the New Technology File System, is a file system that Windows OS uses. It offers features like file and folder permissions, compression, encryption, hard links, symbolic links, and transactional operations. In NTFS, when you make a file, it's represented by a record in the master file table, or the MFT. And for each file record, the MFT allocates a certain amount of space for it. But in this allocated space, the attributes of the file are found. Take a look at some of these. These are all pretty cool in their own rights, but the one we're going to pay special attention to is the data attribute of our file. This is the content of our file. This is the data of our file. And why do I bring this up? Well, NTFS has this really cool thing that it lets you do, which is the ability to define your own alternate data streams. Meaning, you can have hidden information or even an entire hidden executable put away in a new data stream on a seemingly innocent file. So let's take a look at this. I think that the best way we can figure out what these alternate data streams are by just going ahead and messing around with them. So what we'll do is we'll create a humble text file, right? Nothing to look at, but we'll hide some data in it, and then we'll discuss some little things about alternate data streams, like how we'd go about finding it or get there when the time comes. So let's just start off by creating a simple, a simple file. So when we open up this notepad, we've currently opened up the hello.txt file. In here, if we were just to write our normal message and save it, this is our file. So we can just do, no wait, forgot to. So yeah, if we were to type this out, we'd get our original message. But what if we did the same thing, except we write to an alternate data stream? Let's see what that would look like. So we start off by putting in a colon and defining the name of the data stream. And the reason we do this colon, if we take a look at this post from MSDN or Microsoft, we can see that these streams take on the following form. So we have the file name, the stream name, and the stream type. When you do a regular file, the stream name is empty. And this is just a default behavior. This is just, if we were to define it, start off by doing this. We don't have to put in the stream type. Let's do, we save that, and now we can see, hey, wait, we wrote to something, where the hell is it? If we do a dir, it's not being shown here. And how come? Well, the command that we used to list the directory and include the streams, the data streams, or the alternate data streams, is with the /r. So, and if we look at the documentation once again for dir, we can see that the /r is just a way for us to display the alternate data streams of the file in our directory, and that's what we're doing here. So if we do, well, would you look at that? There it goes. And so, and even if we open up a directory to here, we don't see anything out of the norm. We don't see that alternate data stream. And even if we do open this, we just get our regular ass message back, right? Or we get our hidden message. We've covered how we can add these, and there's no limit to how many we can add, but how would we get rid of these alternate data streams, or how would we seek them out? Well, there's a couple of ways we can seek them out. Number one is using this tool by Microsoft called Streams, which will enumerate these streams for you, alternate data streams in a directory or a file. Or like with GetItem, as we can see on Malwarebytes blog over here, GetItem or search, all this stuff. The way that we can remove these is, first of all, by deleting the original file. That will get rid of the streams. Or if we move a file with all these streams attached to it onto a file system that's not of NTFS, because remember, alternate data streams like this are only a feature of NTFS. So what we could do is, I just open up my USB here, and I'm pretty sure this is, yeah, so it's exFAT. So basically, if we try to move this file onto here, it's going to strip that alternate data stream from it. And let's try that real quick. So you move the file, but if I pop it up here, there's no more alternate data stream, no more. If we were to do this, if we were to move this through like actually dragging and dropping it, we'd actually get a little message. So let's try that as well. You see, we get this little pop-up warning that says, are you sure you want to copy this file without its properties? Its properties that it's referring to here are the alternate data streams. And we can say, yeah, and once we do, goodbye alternate data streams.
How about we get to making self-deleting malware now?
While I program this out, I'm going to do this in a manner which combines everything that we've learned so far. For checking to see if we're being debugged, we'll be using our own custom assembly PEB detector. To get the last error value in case something goes wrong, I'll use our custom GetLastError function, which just reads the last error value from the tab. You see how everything comes so nicely together? Alright, it's finally time for us to figure out how we can make this malware that will end up deleting itself. We talked a bit about data streams, right? And that's fine. The way that we're going to make our program delete itself is by renaming the default data stream to another name and then deleting that newly renamed data stream, which will make our program disappear. Well, be erased even while we're running it, which on other normal circumstances that wouldn't be possible, as we've seen. So there are a lot of moving parts. We've only covered one tiny aspect of importance, like the data streams, but there's a lot more to this. So just bear with me while I program this out, and I'll just do what I always do, which is program something out and explain what it is, why it's necessary, okay? Get strapped in, guys. It's gonna be a long one. Now, there are a lot of names I can choose for this project. Most of them will probably get me banned off of this site. It's just a joke. I'm just gonna say something simple, you know? Let's just call it Operation Game End. Now, like I said, we're going to be doing this in such a manner in which we consolidate all of the topics covered in this video by including everything. For error handling, we're going to do the custom function that we made in assembly, and then for checking if we're being debugged or not, we're going to do the same thing. So let's just get our project ready for MASM development, or ASM development, before we start doing all that jazz. Alright, so in our last error function, we've already covered this, so I'm just going to copy and paste this. Cool. And for our debugger, same thing, except we're going to get rid of the patching line, just because, you know, we're just checking to see if we're being debugged or not right now. So we have our two custom assembly functions. Now what we could do is, well, firstly I'm going to put in all my macros and all that stuff. Okay, so the first thing that we want to do is define out a new name for our data stream, right? Remember how the syntax of streams are, and then we're gonna externally define our functions. What I'm gonna do next is make the debug checking thing into its own function, so we can just call it within main. Alright, very standard here. We're just checking to see if we're being debugged. If we're being debugged, this will return true as bool, or it will return false. So let's just do a main setup. Let's just see what that returns. Let's just start it with debugging. Why did it fail? For God's sake. So now if we run this, we'll be able to see that it's working properly. Without debugging, it's not being debugged. If it's not being debugged, we'll have it execute our payload, or without debugging. There we go. In the case that our program finds out it's being debugged, we're going to have the self-delete function run over here. Or I guess we don't even really need to return anything here because we're going to have our function deal with that. Let's start working on our self-delete function. Well, let's just start initializing some stuff. Okay, well, relax. Don't freak out. We're going to talk about these. These are necessary for us to define because we're going to be using them. So we'll start off doing this one by one. So firstly, in this function, we're going to be getting a handle to our file. And because of that, we're going to have to initialize a handle to the file. Next, we're just going to typecast our stream up here into a wide char, just so that we can use it with our functions later. What we're going to do as well is take the path size of our file, and we're timesing it by 2 because we want to get the path size for ychar. Okay, now we're going to start talking about some of these. We can see that there's a pointer to a file rename info structure that we've initialized to null. P file rename info thing. Here's what it looks like, and then you can probably see why we're using this here. As you can see, this contains the target name to which the source file should be renamed. So because we're going to be using this function, we're going to supply it with the file rename info structure. And over here, you can see that there's file name length and file name itself. And that's what we're going to use to change the name of the file. But if we scroll down here, for this file name member or field, we can see that it could be one of the following: an absolute path, like a relative path to the process's current directory, or the new name of an NTFS file stream starting with colon. Do you see what we're about to do here? That's why we include this. Nextly, it's not even a word, we have this file disposition info. Well, now what the hell is file disposition info? Well, also, before getting to that, we have this rename size, and this is just the size of this structure with the size of our data stream name, and it's just for some space stuff after. What is file disposition info? We can see that it's only got this in here, a bool delete file. So like, what is this? From the MSDN, this structure, it just indicates whether a file should be deleted or not. Use only when we use this function. We've seen this for the second time now. This is going to be our main operator. And we can see that if we set this to true, file disposition info will mark the file for deletion when we close the handle to it. So firstly, what we'll do is we'll allocate a buffer for some structures just for the file rename info, just to make sure everything's working. There's no memory related stuff. And I'll use these little comment separators, I guess, just to make it easier for us, because this is going to be a pretty lengthy program. So over here we can see that we're making a call to heap alloc. The first parameter is just a handle to the heap from which the memory will be allocated. You can get it from heap crate or get process heap function, which is what we've been doing. These are the allocation options, the second parameter. And if we do heap 0 memory, it basically allocates the memory but then initializes it to 0. And then the last parameter is just how many bytes. We'll also do some error checking because I want to get to use our function, and it's also good just in case something goes wrong. Right, so I'll also be littering this with a bunch of like debug prints just because I want this to be as clear as possible. If you get annoyed at how much I'm putting this out there, it's for the sake of clarity. In a normal program like this, I don't think I would have this many, but yeah, allocate some memory for the file rename info structure, which is just the combination of file rename info and the new stream. So it's a little bit more than just file. Next up, we'll just also clean up some structures, just to get it primed and ready for us to use. All right, so I say we're going to clean up some structures, and then we're going to zero out the memory, and we're going to zero out the file disposition info structure as well. And with that done, we're ready to use all this stuff. So the first thing I want to do is set this member, this Boolean member from the file disposition info structure, to just have it set to true. So that way we can indicate that the file is going to be deleted or should be deleted. Okay, so let's do that first and foremost. So yep, set the file for deletion. There we go. And I'm sorry that I'm not coding this through and through. I'm going to try to explain it line for line. It's just if I do that, this video will literally get 14 world records straight away for length of media. Also, it's a bit in the ass to edit. So, okay, next up, what we're going to do is in the file rename info over here, we're going to initialize those two members that we had to do, which if you remember, there was two things in here of note, which is the file name length and the file name itself. And these are the two next things that we're going to set. Let's get on that. Right, so you can see, first things first, we set the length of this member, the file name length, to the size of our new stream, which at this point, is just over here. Right, there we go. After that, what we're going to do is take that new stream and then write over the file name. So basically, we're overwriting the file name with our data stream. And once we've done that, we can print out the value of this member to see what it's going to be. Okay? Now, after this, what we're going to do is get the current file name. An RTL memory copy is just a very glorified version of memcopy. You're basically just copying some memory from your destination, putting it into your source, but you also have to define how big it is. And that's basically what we're doing, right? We're trying to take our new stream member and overwrite or copy it over to this member or this address. I hope that's making sense. Next up, we have to get the current file name. And this is just for us later down the line. We're working with wide chars, and this is just an easy way to do that. It gets the fully qualified path for the file. It contains a specified module. So if the first parameter, if we set it to null, it just gets the path of the executable file of the current process, which is what we want it to do. And then the second parameter is where we store that path, which is going to be in our path size. Kind of weird naming, but I guess. So as you can see, we're getting the fully qualified path of the executable, and we're putting it into here. And if that fails, we get to use our lovely custom error function again and print out the value. Now, this is where it starts getting juicy. So what's going to happen here is we're going to get a handle to this file. After we get a handle to that file or this file, what we're going to do is use this function on it, the set file information by handle function. It sets the file information for a specified file. So we can see the first parameter is the handle to the file. The second one is a file information class. So this is the type of information that we want to be changing or setting for our file, and then a bunch of other stuff, which we'll talk. This we can see for the second parameter. So the enumeration class for this file info by handle stuff, there's so many of these. There's a file name info, file disposition info. Remember, Remember, this is just setting it for deletion. And then there's also the file rename info. Where the hell did it go? If you look at file rename info, what we're going to be doing when we call this function and we set the file rename info for this file info by handle class, we're just going to be setting the file's name. So we get a handle to the file. We call set file information by handle on it, and it's going to be using the file rename info structure. And we're going to be supplying our file name length and our file name. And our file name is just an alternate data stream. Now, after that's done, what we do is we close the handle after this function. We do that because that's how we really confirm our changes with this, because this function will set information for the file or make a change for it. And then depending on what we do, sometimes it works when we close the handle to it to really crystallize that change. So after we close the handle to this, what we're going to do is open another handle to it. And once we do that, the change is going to be made and we're going to be opening a handle to this file that's got an alternate data stream in it now. Let's get started on that. So we start by getting a handle to the file, right? This is where we start the actual renaming process. We're using create file. The first parameter is the file name, in which we specify our path size, which by now would have been populated by get module file name. Remember, it's going to store the full path of it into path size, and we're using that here. When you're doing a delete file thing like this, the minimum amount of access rights that you need is delete and synchronize. And so that's what we're supplying here. So you need this delete. Next up, let's take a look at this function in MSDN. Now we're going to be supplying it with file share read. This is just setting the sharing mode of the file. It just tells you what you're allowed to access or not. So if we do something like file share read, which is what we did, we're allowed to open operations on the file or request read access. Otherwise, no process can open the file or device if it requests read access, which is what we have here. The next parameter is just this attribute stuff. Okay, so this parameter over here where it says open existing, this one's kind of fun to learn about. This is just what happens in the event that a file doesn't exist or it does already exist. What do you want this function to do? We're only going to open the file if it exists. So it says open existing. Opens a file or device only if it exists. So that's what we're going to be using here. And the rest two are just null. Flags and attributes and the template file, which we don't need. Remember, this is create file is one of the only Win API functions that I've seen so far that actually return invalid handle value. So that's why we're having it set to this. And then we fancy print out our little handle to the file. And then we say, I guess this should be called renaming is probably better. This is where I was talking about it. So we use this function, right? We're going to set the information on this file. We get the handle to the file. We give it, and then we use the file rename info. This is the guy with the file name, right? The file name and the file name size. And that's what we're setting here. So after this, we would have effectively given our file the data stream and set that for it. And to actually push out the changes and quote unquote refresh this file so that it actually, does this change, we close the handle to it, because this function, you set a change to it and it'll change on exit pretty much, or change on handle closing. And so that's what we do. So after we close the handle on it, it would have had this new alternate data stream. And we had the mark file for deletion here, but this over here, this brand new section, this is where we actually, what the hell is this? Now this is the point where we actually delete the file. So what's happening here is, because we're going to get a handle to the file again, because at this point we already discussed it. The changes are going to be set after the handle is closed, so that it refreshes it. And now when we open a handle to it again, we have a handle to the file with the alternate data stream on it. There we go. And then what we're going to do is use this function once again, except instead of doing a rename info, what we're doing is the file disposition info. And if we remember, file disposition info, all it does is set a file or mark a file for deletion. And we've already set that to true, right? Since we've already set that to true, what's going to happen now is it's going to run that. And if it works, it's going to set the file for deletion. Like actually set it, because we didn't do that here. All we did was we set this member of the structure to true, but over here is where we're actually pushing out that change or trying to make that change. And then once that's done, remember, because it's like set file information by handle, the changes kind of work when you exit out. We're going to close the handle to it, and by then, once we close this handle, the file should have been deleted. And we also just do some regular cleanup, freeing the allocated heap buffer and all that stuff, and closing the handles to the file. And with that done, this is it. This is all our program does. I know it's a bit crazy looking. It's probably because of the bunch of debug prints, but take a second or two to rewatch it if you don't understand this. It's not that crazy once you understand what's going on, and it really clears up once you go into depth with these functions, and you really understand alternate data streams and stuff. What we can do now with this function created is, okay, a debugger is not present, execute our payload, but if a debugger is present, we'll self-delete. So let's do that. And this will already exit for us, so we don't need to do that. And now, if we run this, oh my god, I'm so excited for this. Okay, so if we run this normally, it's gonna run our malware because we're not debugging it. Look at that, right? Executes our payload, exits properly. And now, if we run this with the debugger, let's see what kind of output we get. Okay, alright, so yeah, holy shit, this looks so cool. So we start off by getting the PEB, we check for the debugger presence, we see that we are being debugged, and because we're being debugged, we're gonna self-delete. So what happens in the self-delete thing, right? We allocate the heap for the file name info. We clean up the structures. After we're done that, we set the file for deletion. We don't push that change, but we just set that file disposition info boolean member to true. After that's done, we change the name, the file name length. I guess, hold on, I printed that out wrong. Let me just, okay, yeah, not file name length, file name. Sorry about that. So ignore it. Let's just run that again. Set the file name of this structure to our alternate data stream, and then we overwrote this original one with our new stream over here, right? And it prints out weirdly, but you get the gist of it. And then we get the current file name. This is just going to be populated over here. We get the file name, which we put into this variable here, class size. Badly named, I know, but whatever. And then we start the renaming process, right? First, we get a handle to the file. This is the first handle we get on the file, and then we start renaming it. What happens here is we use set file information by handle with the handle class, and this is just where we push out the name and length of our data stream, right? And after that's done, we close out the handle to push a change, and that's done. We get a handle to it again, except this time we use the file disposition info instead, which will mark it for deletion because we already set the value for that to true. And once that's done, all we have to do is close the handle once again to push out the change, and it should have deleted the file. Let's see this in action. Well, I mean, we've seen it run, but let's actually see this in action. All right, so if we run this normally, right, cool, awesome. There's our executable. Now let's run this with the debugger. Say we are an analyst right now. I'm going to see this. Oh, okay, I want to debug this. Let's see what it does. It just deletes itself. It's gone. It's gone. Let's do that again. I'm sorry. Oh, it deletes too fast before you can. Okay, it deletes too fast before we put in the get chart here. Just put that there just so we get a little buffer time. All right, look at that. Right, it's right there. And now it's like, oh, press enter to exit. It's gone. There. One more time. There it is. There it is. Press enter to exit. Right. And guys, that's it. That's all there is to this. It's so cool. This is such incredible stuff. Like all the stuff that we've done to get to this point. We've looked into the inner workings of the PEB and the TEB and then NTFS and data streams and all that combined into this. Nice. You know the couple of anti-debugging techniques that we literally just talked about? Well, that's not even close to how many you can find covered in the course modules on MalDev Academy. So once again, make sure to check out the first link in the description or the pinned comment below to get 10% off your order and start becoming an anti-debugging wizard right now, as well as leveling up your skills as a professional malware developer. A huge thank you once again to MalDev Academy for sponsoring this video. And this brings us to the end of the video. Thank you guys so much for watching. I know that the headcanon was supposed to be MalDev Part 3, but I wanted to get this video out before that one as a little treat to you all. And don't worry, MalDev Part 3 shall be out eventually. But for now, I'm going back into hibernation. See ya.